you guys, right now, that's about as complicated as it gets for Gay-Lussac's law. Now, let's talk about the next law. In this case here, in your book, they call it.
It's that's avocado.
What's your answer supposed to be?
Avogadro's law. And you know what? Again, you know exactly what this law is all about. I'm going to tell you right now that Avogadro's law is based upon this, and I'm going to write the symbol down for you, N, which stands for moles and volume. Moles. N stands for moles. In fact, in all the equations we use from now on, whenever you see the letter N, they're going to be talking about the moles of something. Because there's a formula out there which we're going to get to is PV equals nRT. N stands for moles. Okay, so that's just the way it's going to be from now on. Like in physics class, whenever you saw the letter G, it meant gravity. Okay, N means moles. Now, here's my question for you. And this is going to sound so simple it's ridiculous. I've got a balloon here. Okay? And let's say, for example, I know the size of this balloon is exactly 1 liter. And inside of this balloon, I have exactly 1 mole of neon. Now, let me ask you this question. And it's going to be really difficult for you to figure out. If I were to place in here another mole of neon, what would happen to the size of the balloon?
Would it increase?
It would get bigger. You bet your sweet book it would. So guess what? You've just found the relationship between the number of moles and volume. And that is, there's a direct relationship between the number of moles of gas and volume.
Is this with everything?
There's a lot of direct relationships. Boyle's is the only one so far that's inverse. Everyone else seems to be direct. So here we go, guys. There's a direct relationship between number of moles and volume. So N and V is a direct relationship. As one goes up, the other goes up. The other one goes down, the other one goes down. Boy, oh boy. Now this may be tough. This may be extremely tough. But I gotta ask you this simple question here. Can you kind of give me the idea of what you think the mathematical formula for this would be? Proportion. And what would the proportion look like?
Would it be N1 over V1?
N1 over V1 equals
N2 over V2.
N2 over V2.
You might have to repeat it for the cheerleaders.
There it is.
Repeat it for Brianna also.
What's that?
I heard it, man.
Because you know she's still a cheerleader.
No, I ain't.
Once a cheerleader, always a cheerleader.
I might do cheerleading in college.
Oh no. Oh no. Alright, but anyway. I don't think I have to sit here and do this math problem for you. I think you guys can do this on your own. Okay, this isn't very complicated. So far we've gone through 4 gas laws.
What?
Okay. So now let's talk about the 5th gas law.
Yay.
This one has a very unique name. Oh my God. It is called
JJ.
Now, here's the combined gas law. The combined gas law is Boyle's, Charles, and Gay-Lussac's law as one major equation. I can put all 3 gas laws together.
You can do that?
So they just left out.
Yeah, they left out Avogadro.
Why?
They didn't like it.
He got the
He's a strange looking dude. He got in there and they go, no, I ain't getting in. I get in there.
But this dude has a name.
All right, guys, I want you to do this for me. Can you go back and tell me the mathematical formula for Boyle's log n, please?
B1,
V1,
B1
V1
equals
equals
B2.
V2,
P2.
P2. Okay, so there's Boyle's law. Can you tell me Charles's law?
B1
Okay, V1
over Ti.
over T1
Yeah, there we go. Equals B2
equals V2
over
over T2.
That's cold.
Can you tell me what Gay-Lussac's law was?
P1 over Ti.
P1 over T1
Okay.
equals P2 over
That's
T2.
cool.
And there you go, we just found the combined gas.
There's nothing squared in there.
Why is you so amazed, Joanna?
Because, like, they all just combine together that easily.
Yes.
Combine.
Now, here's the interesting part. This combined gas law can be used to solve Boyle's, Charles, or Gay-Lussac's law independently. Okay? The only thing that doesn't change here is this, the number of moles of gas present.
So it stays constant.
Stays constant.
And stays.
N is equal constant. Now, that's why it's not in the formula. Okay, if it was in the formula, we just have another letter up here, we just put it up there and then that'd be it. Now, here's the interesting part. I can solve an equation using the combined gas law. If you guys remember back, we had a problem that looked like this not too long ago. I had a container, an aerosol spray can. Okay.
Yeah.
Oh, I changed it to a nozzle? Okay. It doesn't look any better. All right. Now, here's the things I know. Again, the temperature here was 21 degrees Celsius. The pressure inside here was 27.9 pounds per square inch. I said that the original volume of this container was 300 milliliters. And I told you that the temperature was going to go up to 500 degrees Fahrenheit, or we did figure out it's 533 Kelvin.
Right.
So I'm going to leave this as 294 Kelvin to begin with. Now, we use Gay-Lussac's law to solve this problem. Correct?
Yeah.
Now, we could have also used the combined gas law. Because in the combined gas law, V1P1 equals over T1 equals V2P2 over T2.
P2.
What do we know about the volumes in both of these cases here?
300.
They're both 300.
Right.
So therefore, if I went 300 milliliters here and 300 milliliters here, guess what happens mathematically? They cancel out.
What?
Because remember, they're the same on both sides?
Right.
And so just by using the combined gas law, I can plug in all the numbers I have and then just do, okay, oh wait, 300%, can't get rid of it. And what are you left with? P1 over T1 equals P2 over T2.
Okay.
Which just so happens to be Gay-Lussac's law.
What you listening to first?
And we solve it exactly the same way.
Joanna.
Now, how would you use combined gas law for other things? Well, what happens if I told you the following? I have a container. I have a lot of containers and I can get rid of all of them. Okay?
Why do you have so many?
There's my container. And I know that the volume of this container is 2 liters in size. The temperature of this container, just for simplicity's sake, is going to be 300 Kelvin. I'm going to give it to you in Kelvin already. The pressure inside of here is going to be 800 millimeters of mercury. But here's what happens. This object gets put into a trash compactor, and the volume decreases to 0.5 liters, and the temperature changes to 400 Kelvin. Can we figure out what the new pressure would be inside of this container if I were to change both the volume of the container and the temperature of the container?
Mm-hmm.
Which gas law you want to use?
The combined.
You're going to use the combined gas law because all three things, volume, temperature, and pressure, are all changing. So, start plugging away. Start plugging and chugging. Pressure is in terms of millimeters of mercury in this case. Because remember, if you go back to back in August, we gave you all the units of measure of pressure, all the standard pressures. Okay, so you're going to have to, kind of familiarize yourself with those values again.
Oh, we're trying to find, he said,
So we're trying to find what would the new pressure be inside of that container. What is P2 going to be?
4,000.
No.
Hey, Felicia, that's
Can we at
Hey,
least?
Felicia.
Yeah, don't even give us a chance.
some people cheat right off the whole problem. And off the spray can over here.
So I'm going to go 2 times.
How many? What? So what decimal point are we going to? Mr. Adrian.
Go. Give me 3 sig figs.
Okay. Well, you should.
Shut up, Salon.
What if I don't want to put in sick pay? Oh, you just said, oh, okay.
Yeah, I said let's put 3 sig figs on it. And if you did, you come up with 4,270 millimeters of mercury. If you wrote down 4,266.6666666666666
Seven.
6666666666666. No, actually, it's a repeating decimal. It's 0.66 forever.
Oh, well.
That 7 just means your calculator going, okay, I'm rounding. Okay. Problems. Confusions. Okay, next gas law. There's like 7 or 8 of them.
How are you doing?
We're going to try to get through them all. So that, therefore, when I give you the homework, there is no excuse for you saying, I didn't learn that in school.
Why would you give us homework?
Alright, so here we go. This gas law here, let's go with,
Why are you on my phone?
let's go with this one here.
Dalton.
Dalton's low.
Dalton.
Dalton.
Shut up.
Now, here's an interesting part about Dalton's law. It's also called Dalton's law of partial pressures. And this is important to us because when we do our labs, we're going to have to take this law into account. Okay? Now, I'm going to let you see if you can figure out how this would work. Okay? I'm not going to tell you anything. I'm just going to draw a picture. Here is a container.
What type of container?
Here is a container. Inside this container, there are 2 gases. There are neon and there is argon. The pressure inside this container caused by neon is 1.5 atmospheres. The pressure caused by the argon in this container is 0.5 atmospheres. Here's my question. What is the total pressure inside this container?
2.
It is 2 atmospheres. How did you get that?
Yeah.
So you just found out Dalton's law. It says the total pressure, P sub T, is equal to the pressures of each gas present in the mixture. Well, yeah, it is kind of obvious. Now, you notice something about this one here. What never changed? One, the volume did not change. What else did not change? The temperature did not change. What else did not change? The number of moles did not change. So in this case here, I didn't change anything.
So this can only work assuming that none of those other things.
Yeah, none of those other things have changed.
And if you're like given a work on one state, will volume temperature will remain constant, or they just won't talk about it?
They just won't talk about it.
So then you just have to assume.
Yes. A lot of times they'll just debunk it and say that's it. Now, okay, so you guys get this thing here?
Mm-hmm.
Okay. Does it seem hard and complicated?
No.
Okay. All right, try this one here. What if I told you I got another container here? I got lots of containers. Inside this container here is going to be, okay, neon gas, argon gas, and krypton gas. Here's what I know. The total pressure of these 3 gases comes out to be 9 atmospheres. This is going to be tough. The pressure caused by the neon gas is 5 atmospheres. The pressure caused by the argon is 1 atmosphere. What is the pressure caused by the krypton gas?
3.
In this case, it must be 3 atmospheres. And how did you get that?
Shut up.
Yeah, you just added and subtracted.
Brianna, it's not 2 atmospheres.
Shut up, I put the wrong guy.
Why are you trying to be lucky?
That's not fair when you so.
You know, did you know?
I put the wrong number. I knew the answer.
All right, questions? Now, in our case, when we actually get into this, we're going to use combined gas law, or this is Dalton's law of partial pressure, in this way. The total pressure is equal to the pressure of the gas plus the pressure caused by the water vapor. And that's going to come later, but this is basically, I don't have to put 1s and 2s in here. I can actually put the substances I'm talking about. This is Dalton's law of partial pressure. Because it says the total pressure is equal to the sum of the individual pressures of each gas. That is exactly Dalton's law if you want to write it down.
But, so water and the gas are not measured in the same.
If I talk about water vapor, yes. Then
Is that
there,
what you just put the V right?
yeah, I just put the V there to represent it was vapor.
Just saying if you put.
It says that the total pressure in a mixture of gases, the total pressure in a mixture of gases is equal to the sum of the individual pressures of each gas.
It's equal to what?
The sum of the individual pressures of each gas. Which makes sense, hopefully, to you because of that stupid thing I did right here. Okay? Total pressure is always equal to the sum of the individual parts. That's it. No matter what. Now, I will tell you this. That if I were to change, now this is something that's going to be interesting. If I were to change the pressure of this to 2 atmospheres, this pressure and this pressure would not change. The pressure caused by the neon gas is just the pressure caused by the neon gas. They're independent of one another. So if I added more argon here, yeah, the pressure would argon go up, but it wouldn't change anything in here or here. It would change the total pressure, because now the total pressure would be 10, but the pressure of each gas here, this pressure and this pressure, are unaffected by the pressure caused by the argon gas. In fact, if I went in and took out all of this and all of this, just got rid of it, guess what the pressure of the neon gas would be inside that container? 5 atmospheres. Okay? They are independent of one another.
Okay.
So therefore, if I say I want to change one, fine, change it. It doesn't do anything to the other ones. Okay? Does that make sense?
Yes.
Alright. Okay. Well, that was all the pressure center. Let's go on to, let's see, we got Dalton, we got this, we got that, we got this, we got that, we got this,
Shut up.
we got that. Oh, hey, let's do this one here.
What's his name?
Here, 8 a.m.
His name's Graham? Graham.
Graham crackers.
Okay. Now, Graham's law is a little bit trickier to understand, but not quite. Now, here's something you need to know. Temperature is the relative measure of the amount of energy a particle has. Write it down. Temperature is the relative measure of the amount of kinetic energy a molecule possesses. Of kinetic energy a molecule possesses.
Is the relative
Measure of the amount of kinetic energy a molecule possesses.
Can you repeat it one more time?
So, here's what I know. You ready?
I'm so serious. I don't know how to
P-O-S-S-E-S-S.
What?
I was so serious.
I just-
I know he
Okay.
put them.
Now, here's what that
That's
means.
not.
I know that, yeah.
I will tell you right now that inside this pen, molecules are moving. The reason is because this has a temperature. Okay? The amount of kinetic energy that the molecules in here possess is equal to the amount of kinetic energy the molecules in this room possess because they're at the exact same temperature. Okay? That's it. That's basically the basic idea here. So let me ask you a question. What if I had two gases? Well, let me go back a second. So temperature is related to kinetic energy. Okay, now dig out your physics hat for a second. Can you tell me what the formula for kinetic energy is according to physics?
Wait, ain't it like
Kinetic energy equals
K equals like, ain't it G something?
what?
Is it G, look, it's G,
And put it in T.
G, P-H over,
Good, you don't know.
It says Omega.
one of them, shoot.
Hey, today's the problem. I didn't know. No.
This is the mathematical formula for kinetic energy. Kinetic energy equals 1/2 mass times velocity squared.
I remember that.
Okay? Are you guys with me so far?
Yeah.
Okay.
No.
Now, remember, temperature is kinetic energy. Okay? So, let's say, for example, I've got the following thing that I want to do. I'm going to kind of paraphrase here. Kinetic energy just means energy of motion, or the ability to cause change. Okay? So what I'm going to do is I'm going to do two things. Number one, I'm going to take this, and you're my guinea pig, so you come up here before the camera so they can see you. Okay? Now here's what I'm going to do. Squat down just a little bit. What I'm going to do is I'm going to drop this on her head from this height.
Oh my God.
Now, what's going to happen when it hits her head, certain things are going to occur. Will she be damaged?
Yes, absolutely.
Yeah, she'll have a bump. Well, you thought I was going to do it? I know, wait a minute. Now, I want you to think about that. It's going to hurt, right? Now, if I wanted this marker to cause the same amount of damage, will I hold it at exactly the same height above your head as I did those staples?
No, because you need more velocity.
Because I need more velocity.
What?
So here's what we know. Very good. And see, it didn't even get hurt. Now, if you think about this, why did you need more velocity for this object to hurt her as compared to this one here?
Because the masses are different.
Because the masses are different. So here's the question. If I want these two subjects, these two objects to have the same kinetic energy, which one has to be moving faster?
The marker.
The light one. Okay? Now keep this in mind. I've got two gases that I have. Okay? One gas here and one gas here. What's that?
You drink that gas every day?
I drink that gas every day. All right, now what's going to happen is, let's just assume the following, okay? This gas here is hydrogen cyanide. So I have a new gas, and that gas is HCN, hydrogen cyanide. I will tell you that if you inhale this hydrogen cyanide, you will die instantly. I am immune because I've been here long. Okay. Now, the second gas that I have here, okay, is going to be ammonia gas. Okay? Ammonia is at H3. And you guys know what ammonia smells like. Now, my question to you is this. If I open these containers at the same time and let these gases begin to move, they are going to basically travel throughout the room through a process called diffusion. And diffusion is what? Shh. Okay, it is the movement of molecules or substances from an area of high concentration to low concentration.
What is hungry?
That's Dr. Siegel. Do you guys have Sieg?
Yeah.
You were the last group that had Sieg, huh? Okay, so anyway, you guys had the song with osmosis and diffusion, and you know, osmosis is diffusion through a semi-permeable membrane. Okay, now, think about this, guys. These two gases here are at the exact same temperature, which means that the speeds of the molecules, are the speeds the same? No. Why? What is the same?
The velocity? No.
No. What is the same?
Their mass?
Their temperatures are the same, which means their kinetic energies are the same. Now, if that's true, if these start to diffuse here, one of these gases is going to be moving at a faster rate than the other one. Why? Because if you have the same kinetic energy, the lighter the gas, the faster it must move to keep the same kinetic energy as a heavy gas. Yes?
Yeah.
Now, if that's also true, if one of these gases is much lighter than the other one, it should reach your nose first. So here's my question. Which one of those two is the lightest gas? Is the hydrogen cyanide the lightest, or is the ammonia the lightest? How would you determine that?
Formula mass.
Formula mass. Good. Now get the formula mass of these two substances.
Wait, ain't it gonna be the...
What's that?
Ain't the ammonia gonna be the one that's the lighter one?
I just like.
Just
But I
like...
want just to do numbers because then we're going to do some math work with it later.
Hydrogen. No, I'm not. It's ammonia. What is it? The hydrogen cyanide?
The cyanide...
Yeah, you calculate
the
it, give me
hydrogen
the exact
cyanide
weight.
is automatically the way more.
Good. I'm not done yet, because you're gonna be doing math work, because I wanna know how much faster is one than the other.
Bro,
I want to know.
that's too bad.
No, actually, no. If I want to know how many times faster something is. Okay. So anyway, do this work for me, okay?
Ain't it 00794?
No.
No, I'm saying that for the hydrogen. Look.
Why don't you just look at your periodic table?
Shut up, I am.
Just look at the periodic table. If you're not sure, you should know.
Whatever.
Put down here.
I want to be better without using it.
Find out.
Roach. Ouch.
27.02534.
You talking?
Play 03.
No, you pay the period. What part?
17.03052.
Point 03052. What? Check the time.
So here's what we know automatically. Felicia? So here's what you know automatically. Which one are you going to smell first?
The lighter one.
The lighter one, which just happens to be ammonia. All right, now what I want to know is this. How much faster is it? How many times faster is it?
You gotta put it into that equation and plug them both in and then.
Okay, well, now, what I'm going to do for you is I'm going to show you kind of like a shortcut. Okay? And here it is. This is the formula for Graham's law. And it states the velocity of the light gas as compared to the velocity of the heavy gas. The ratio of the velocity of the light gas as compared to the velocity of heavy gas is equal to the square root of the molar mass of the heavy gas as compared to the molar mass of the light gas.
This square root symbol is extra nice.
And all it's saying here is
Joanne's
that light
calculating.
gas moves faster than heavy gas. So what I want to do is figure out how many times faster ammonia is as compared to hydrogen cyanide. No problem. So here it goes. The velocity of ammonia as compared to the velocity of hydrogen cyanide is equal to the square root of the mass of hydrogen cyanide, which was 27 point, what is it?
02564 over
Divided by
17.03052.
Okay? So now what I want you to do is I want you to take those two, divide it, and then take the square root of that number. So 27.02564 divided by 17.03052, and I'm going to raise that to the 0.5 power, because taking the square root is the same thing as.
Remember, don't let Mr. Peterson hear that you won't remember that.
No, because I came into the middle of the thing. I didn't
The
know.
number is 1.26. And now here's what this means. The answer comes out to be 1.26. It means that ammonia is going to travel 1.26 times faster than cyanide.
So, what was units which you put on the
There are no units for ratio. There are no units for ratio. Felicia, somebody wake her up, please. What? Is she sick? She was yelling and all that stuff 2 minutes ago. So there's no.
Well, let that would have been me. I would have got the.
Oh yeah, that's right. Okay. All right, now, I want you to also think about this. This is going to be important in a couple of questions you're going to have to answer.
Aerosol.
No. This is not another aerosol can, this is a tube. And what happens here, this tube here is, we'll put this as 6 meters in length. This is still part of the problem.
Oh, this is the same problem?
This is still part of Graham's law.
Oh,
Because I want to show you what this means.
it's 6 meters?
It's 6 meters long.
It's like a minute.
Now, there's a couple things you need to know here. If ammonia is traveling 1.26 times faster than that of hydrogen cyanide, it means the following. That if I put ammonia down here, NH3 down here, and hydrogen cyanide down at the other end, the distance ammonia will travel will be 1.26 meters in the same time it takes hydrogen cyanide to travel 1 meter.
Maybe we do something like this.
Something similar. All right, now here's my question for you. Where would these two gases meet inside this tube here? Where would they meet inside this tube?
Closer to the...
They
no,
can't meet in the middle, correct?
No, it'll be... on
Because the
the
only
side.
way they could meet in the middle is if they were traveling at exactly the same speed.
Closer to the hydrogen side.
It would be closer to the hydrogen cyanide side. But how could you figure out its exact location where those molecules are going to meet? Okay, you ready? Think about this. This is the distance hydrogen cyanide travels. And this is the distance that the ammonia travels. The total distance traveled by both of them can only be 6 meters. So if x is the distance traveled by hydrogen cyanide, the ammonia must travel 1.26 times x, which means
We're gonna combine like terms. You're gonna divide both sides by 2.26.
and what does that
You're
come out to
gonna
be?
get 2.65.
Are you thirsty?
So that means at this distance here of 2.65 meters is where both gases are going to meet each other. And it's short of halfway, which makes perfect sense. Does it not?
So they both close to.
Yeah, because they're both kind of close to each other in speed, but this one's going to travel much further, and eventually, at 2.65 meters, from this side here, they're going to meet. So that means that hydrogen cyanide will travel 2.65 meters, so that's the distance traveled by the HCN. How much distance will the NH3 travel? How would you figure out how much distance the NH3?
Track.
Subtract what?
That's 6.
Yeah, good. Take it from 6 and tell me what you get.
3.35.
Okay? Do me a favor, just for the heck of it. Divide these two numbers out and tell me what you come up with.
Wait, which one on top?
Yeah, these
The
two.
one of the lighter one.
What?
This one here up top, this one here in the bottom. Divide those two.
You get the 1.26.
You get 1.26. We get to 1.26 again. So it's basically telling you that your problem is right. We've calculated exactly where this thing is going to meet.
Because you put 2.65 in for the X, and then you subtract that from
6.
6.
Because if the whole tube was 6 meters long, and we've covered this much distance of it so far, what is this distance? And then basically you just subtracted the 2. So that means that this distance from here to here is 3.35 meters, and this one is 2.65 meters. And basically what we should find is the ratio should be the same. Okay, and it is. Okay, there's Graham's law.
This is my socket.
Wait, where do the 1.26?
Can we take a break, man?
1.26 was from here. In other words,
You
we figured out that that the actual ratio of speeds between ammonia and hydrogen cyanide was 1.26. We knew that since ammonia was the lightest gas, it's going to travel 1.26 times further.
Tomorrow, take my
And we just
SAT
proved it.
tomorrow.
I gotta reschedule my detention.
By dividing this number by this number, you end up with 1.26 again. So it's proving the point that, yeah, the ratio of distances is still exactly the same.
So it should always,
It says all your
that's
emissions.
It should always check, it should always be the same ratio as the ratio of speeds. The ratio of speeds. Okay, whew, we are almost done.
What?
And now comes one of the last gas laws we're going to talk about, and that is known as,
Can it be called JJ's?
No.
Why not?
Ideal gas law? That's a
I'm
this
ideal.
one is known as the ideal gas law. This gas law works under normal circumstances all the time. When we deal with real high pressures and real high temperatures, the ideal gas law doesn't work very well, okay? But for normal circumstances, it works quite well. Now, here's the mathematical formula for the ideal gas law. It is
How many bitches can I knock that food out of?
PV equals nRT. Now, here's what we're going to need to know. We know that P, of course, stands for pressure. V, of course, stands for volume. N, of course, stands for moles. And T stands for temperature. The only thing we don't know is R. Now, R is called
Is that
the ideal gas law constant. Write it down. Go ahead, what did you say?
I read the book and it said like something about ratio.
Yeah, and it basically it's a ratio of all three things together.
Whatever.
Now, guys, I will tell you this. R values.
Alright, I was doing my work.
That's good because you're the smarter of the group.
It was just trying to read the book.
Yeah.
Okay.
We didn't understand.
Okay, R, the ideal gas law constant. I'm going to tell you right now that even though it's an ideal gas law constant, there are varying numbers that can fit into that particular value. It all depends upon the units of measure of pressure, volume, and temperature. Okay? Well, temperature is no problem because temperature is always measured in Kelvin. So my question is, how do you go about determining what the R value is to solve a problem? Well, I'm going to teach you how to solve for R first, which then we will use in other problems. How do you solve for R? Well, in this case here, you're going to find that R is equal to PV over NT. Now, what I want to know is this. Can you tell me some standard conditions like STP? Can you tell me what standard temperature is for STP?
I feel like I've written
We have written down STP before.
Hold on.
Standard temperature is equal to 0 degrees Celsius or
No,
73 K.
man.
Very good. Now, let me ask you this question. Do you know what standard pressure is? And you're going to tell me, yes, I know there are 9 different standard pressures.
Wait, hold on. Don't you say nothing. Don't. Stop. No.
here's what I'm gonna do, guys. We are first gonna solve this problem if standard pressure was in terms of millimeters of mercury.
760
In this case, it's 760.
You are the wrong.
So, here's what we know so
Teachers and
far.
students, please pardon this interruption.
Keep going.
Teachers and students,
Get
please
him.
pardon this interruption.
No. Yes.
Are you gonna give me the other?
This is Assistant Principal Mr. Walsh.
No.
Earlier
Yeah,
this week, we
yeah,
made an
yeah.
announcement reiterating our expectations for good
Watch
decision
this.
making inside and outside of
Can
Columbia.
you tell me,
This evening, I would like to take a
can
moment
you
to
answer
say great
this
job to our
question for
student
me?
body.
We've told you
This
this
past week, we
one
were able
time.
to witness our students
1
participate in
mole
several
of any
events,
gas
such as a
at
special
standard
event,
temperature and
basketball
pressure
tournament,
occupies
a
what
basketball
mole?
game, I'm sorry. We hosted
1
Wednesday,
mole
and also
of
the
any
science
gas
fair was also
at
held the same
STP
day.
occupies what
I also want to
mole?
thank our teachers, security, and students for
It
their
is
cooperation and
22.4.
concern yesterday while
So
I
this is
with
22.4,
one of
and
our
this
Oxford
is
students.
1 mole.
Also, if you come to the gym jam tonight,
Yep.
please have fun and be safe.
Okay,
Good luck
here's
to
what I
boys
want you to do,
basketball
yes.
tonight as they play Lincoln Way North at Lincoln Way North.
1 mole of any
The
gas
last announcement is that swim
And
practice is on
STP.
board today.
will
There will
occupy
be bus
22.4
transportation
liters.
home. Thank you and have a safe
This
weekend.
is what's known as molar volume. Now, do me a favor. You see all these numbers?
Uh-huh.
Tell me what's out of the equation, tell me what you get.
Wait. Hold on.
So we have P, we have V, we have N, we have T. Whew, tough. Solve it.
What you just said, Kenesha? Why you want Keep playing. That was so funny.
I said
Didn't nobody ask you? Yeah, okay, didn't nobody ask you? Jesus.
62.4.
Oh, no.
Now, here's what I want you to notice. The answer does come out to be 62.4 or 62.36. Now, the units that are involved in this problem look like this. It's millimeters of mercury liter over mole Kelvin. And the reason is because none of the units canceled. Now, in this particular case, this R value, if pressure is measured in millimeters of mercury, volume is measured in liters, this R value will always be used in that problem. As long as pressures in millimeters of mercury and temperatures in terms of Kelvin. And volume is in liters. And it looks like that's as far as we can go. So you can't get your homework tonight because I didn't finish this yet.
Yay!
You want to do me a favor there, Maestro, and hit the toggle switch?
This one?
No, the other one first.